In this part of chapter 13, we are going to practice calculating equilibrium constants from measured equilibrium concentrations. We need to understand that the equilibrium mixture may have different amounts of reactants and products, but the value of the equilibrium constant will always be the same. The value of equilibrium constant is independent of the initial amounts of reactants and products. This is very important to remember for the current and then future consideration. Let us look at this example. Suppose we have a reaction. 2 moles of A reacts with 1 mole of B and produces 4 mole of C, and these all components are in equilibrium at some moment of time. We are given that initial concentrations of A and B are 1 molarity and the initial concentration of C is 0. Hence, at some moment of time when equilibrium is established, measured concentrations for C is 0.50 molarity. The question is to find equilibrium concentrations, equilibrium molarities of A and B. To be successful in a solution of this type of problems, it's highly recommended to use this technique known as ICE table. ICE table is abbreviation which is related to first letters in names of rubrics: initial molarity, change in concentration, equilibrium molarity. The next step which we need to take, we need to analyze the problem and understand the sign of changes in concentrations. As far as A and B are reactants, the concentration of reactants is going to reduce, hence the sign in changes is going to be negative in both cases. And in opposite, the change in concentration of C is going to be positive because it's a product and it's going to increase in concentration. As far as initial concentration of C was 0 and equilibrium concentration is 0.5, hence the change in concentration of C is the same, 0.5 molarities. Now, let us have a deal with numbers and let us figure out what is the change in concentration of A. The change in concentration of A is proportional to change of concentration of C, and this proportion is hidden in stoichiometry. So 0.50 molarities of C times stoichiometric coefficients. We're looking for the change in A, hence A has to be in numerator. 2A over 4C is going to be 0.25 molarities as a change in concentration of A. What is change in concentration of B? And it's going to be 0.5 again, 0 molarities of C, times this time is going to be B in numerator, or C in denominator, and it's a 0.125 molarities. We need to watch significant figures. Let us incorporate these numbers in ICE table and find equilibrium molarities. It's going to be 0.75 for A and 0.88, remember significant figures, for B. That's it, solved. Let us try one more practice. So this time we have a reaction. 2 moles of methane is in equilibrium with the mixture of products, ethylene, and 3 moles of hydrogen. Initial concentration of methane is known as and equilibrium concentration of acetylene. So we need to find equilibrium concentrations of methane and hydrogen, and then we need to find Kc. Okay, let us start. Our ice table is established with all information which is provided. Now the first step which we need to take, or the next step which we need to take, we need to figure out the signs in change of concentration. So it's going to be negative for methane, positive for acetylene, and for hydrogen, because they're products. Now let us have a deal with numbers. So the change in concentration of methane is proportional to the change of concentration of acetylene, and as far as initial concentration of acetylene was 0 initial, and equilibrium is known as 0.035, hence the change is the same as 0.035. Then the change of concentration of methane is going to be 0.035 molarities of acetylene times 2 moles of methane, 2 moles of methane over 1 mole of acetylene by stoichiometry, just from equation. So the answer is 0.0757, pardon me, 7 molarity. Okay, and same for hydrogen, same procedure for hydrogen. Changes in concentration of hydrogen is going to be 0.035 molarity times, this time it's 3 hydrogens over 1 acetylene, and this is 0.105 molarity. Excellent. Let us incorporate it in our table. So 0.070 for methane and 0.105 for hydrogen. For hydrogen we have the same because we didn't have anything at the beginning, and we have 0.045 equilibrium concentration for methane. And only last step left over is just to set up equilibrium concentration for this process, and this is concentration of acetylene times concentration of hydrogen cubed over concentration of methane squared. Then plug in numbers, which are acetylene, which are 0.035 times 0.105 cubed over 0.045 squared, and answer when you calculate it is going to be 0.020. One more practice. The following reaction is given: 2 moles of nitrogen dioxide is in equilibrium with dinitrogen tetroxide. The signs of the change in concentrations are going to be negative for nitrogen dioxide and positive for dinitrogen tetroxide. If you look at what is provided, you will see that the change in concentration of nitrogen dioxide might be easily found as the difference between equilibrium concentration and initial concentration. And the result is negative 0.0028 molarities, which makes sense, and because nitrogen dioxide decreases in amount, 0.0028 molarities. What about dinitrogen tetroxide? Dinitrogen tetroxide will be found as 0.028 molarities of nitrogen monoxide times coefficients in equation 1 for N2O4 over 2 NO2, and it's going to be 0.0014 molarities. We can immediately incorporate it in our ice table, and as far as initial concentration was 0, then the equilibrium concentration is going to be the same. Excellent. Now we have a deal with concentrations, hence we need to start with equilibrium constant in terms of concentrations, and it's going to be N2O4 over NO2 squared. Now let us plug in numbers, and it's 0.0014 over 0.0172 squared. The answer is 4.7. But we also need to find Kp. Kp has an expression Kc times RT power delta N. And two preliminary steps have to be taken. So first of all, convert temperature in kelvins, which is 100 plus 273 Kelvin. And this is 373 kelvins. And the second step is to figure out what delta N is. Delta N is 1 mole for products minus 2 moles for reactants. It's a negative 1. Hence, Kp is going to be found as 4.7 times 0.08206, which is R, times 373 kelvins, power negative 1, equal, when you calculate it, you will get 0.15.